So to set just a little bit of expectations, this will be a more technical session. We're going to dive into some details. We will go through some definition and business use case context to really set things up, but then go into the technology, dive into everything behind data privacy. So first, Clyde, I really want you to help us differentiate between data security, data protection, and data privacy, right? Protection it comes first because it's really what people tend to think about when this topic comes up, and it's concerned with protecting sensitive information like PII, PHI, PCI, what have you. I mean, that's easy. If you look at James Rice, I have a name, a social security number, maybe a credit card number that are these direct identifiers. But talk us through really what data privacy specifically is focused on and how that is a little bit different.
That's a great question. Cybersecurity as a practice is generally focused on access control. So a firewall, for example, is a form of access control. Router ACLs are access control lists. Authentication, authorization, all of these are ways of controlling access. Data protection is an access control. That is, I'm encrypting the data and only those with rights are allowed to decrypt the data, or I'm tokenizing the data and only those with rights are allowed to detokenize the data. So all of these are methods of access control, and they're concerned with the problem of, are you allowed to see this information, or are you allowed to access this resource? And that becomes a sort of binary yes or no. Data privacy is a condition that can arise even during the normal authorized access to data. So what I mean by that is, I may have information about James, and I've got his email and social security number and credit card number, and I might pseudonymize those in some way, like tokenization or encryption, and I could control who gets access to that information, and therefore I've protected James's identity. But if I am upset at James, I work at wherever the company is that's collected James's information, and I know he's somewhere in my database because he's my friend, and I know what his birthday is, and I know what his postcode is, and I know that he's a guy. Those three pieces of information alone, which are probably not protected in your data set, are often enough to uniquely identify about 87% of people in the United States. So even though we've put the access control in place and said, yes, Clyde is allowed to see this information, no, Clyde is not allowed to see this information, there is an unintended consequence that privacy information has leaked based on what's available to that user. It's an accident almost of this information coming out. And that's why privacy enhancing technologies have become so important.
So, what de identification techniques then does data privacy leverage to be able to protect the postcode, the date of birth, right? The examples that you were giving there.
Well, there are a number of different techniques. One is anonymization. Anonymization often gets used in common parlance just to mean I don't know who you are. And that is a kind of anonymization. But true anonymization means I can't figure out who you are. So I might, put my hands over my face and be anonymous, but because I'm wearing this vest and this shirt, somebody might be able to look at me and say, "Oh, with that hair, that's got to be Clyde." I wasn't really anonymous. And often that's what we find happens when people have tried to anonymize data in the past. There are some really interesting incidents. Netflix once produced a whole bunch of information about reviews that people gave to movies and what movies people liked. But the unintended consequence, even though they had removed the names of and account information of those people, what information remained, what they liked, what they disliked, when they watched things, people were able to infer not only who was the person who had reviewed those Netflix movies, but things like what their political views might be. Now, in America today, that's maybe not a big issue. In some countries, that would be a terrible issue. And the same is true for a lot of other things. The New York taxi cab incident, where they'd published several taxi cab trips. That included the pickup location, the drop-off location, how much it cost, and what the tip was. And the idea was they were trying to show that the tipping was bad in New York. What the unintended consequence that was related there was that people were able to actually get additional information, like who got picked up at that location at that time, and then infer and identify who that person was, and a number of celebrities were exposed as bad tippers. In all of these incidents, there was an attempt to anonymize the data, but in fact, all they did was de-identify a record. That is, they removed the obvious identification of the record, but they didn't take care of the privacy risk of this incidental or indirect kind of identification. And techniques like anonymization are designed to handle that. And this is generally through some form of generalization or aggregation or dealing with averages. Uh, so, for example, we might say instead of retaining the postcode of the individuals, may only retain the first 3 digits of the postcode. So you might know that somebody lives in Columbus, Ohio, but not necessarily what neighborhood they live in. The same thing might be true of age. Instead of giving the precise age of somebody, you might give their general age. It's an age range between the ages of 40 and 45. Or you may give the year of birth instead of the day and the month and the year of birth. Uh, any of these are techniques that can be used to generalize, to fuzz the picture a little bit. And the idea then is that the individual gets lost in the crowd, but the information about the entire crowd is still of value.
So that's helpful, because then that friend of mine that you talked about that's out to get me can't infer who I am based on, exact information on, living in downtown Denver, being this exact number of years old. And instead, having those generalized concepts means that there's a lot of other people in the data set now that look and feel like they could be James as well.
Yeah, that's exactly right. And there are techniques here, particularly things like K anonymity, L diversity, T closeness. They're methods by which you can generalize and then use a privacy model to determine the probability that someone could re-identify an individual in your data set. We can actually quantify how anonymized that data set has become. One of the areas that Protegrity focuses on with anonymization is not only to ensure how anonymized the data is so that we can protect the privacy of the individuals in that data set, but also out of the information in that data set, what is the most important so that maybe that becomes generalized the least and other less important factors are generalized more in order to maintain the anonymity of the individuals but retain as much of the useful information in the data as possible.
So I want to dive a bit more into the tech, but before we go there, I have one last question for you on the business side. I've seen at some of the customers we're working with where data privacy is empowering analytics, for example, and that might be the opposite of what you think. You think, well, if I'm protecting data, that means that more information is locked down, but good protection and privacy doesn't just lock down data. It's actually about making more data available, but doing it in a secure way. So it's enabling more AI and machine learning. It's improving prediction engines. It's getting more data into these pipelines faster. But what are some of the business cases? What are some of the use cases that you see driving this that you think make this really important for an organization to need to adopt some of these data privacy techniques that we'll dive into some more detail on in just a second?
We're seeing massive adoption of privacy legislation across the world. 75% of countries now have privacy legislation. In the United States, a number of states have privacy legislation. And that means that if you have information, privacy information, about a data subject who lives in any of these jurisdictions, then you have to apply their regulations to that data. Privacy enhancing technologies allow us to sort of sidestep that problem. That is, data that has had privacy enhancing technologies applied to it, if done correctly, no longer fall under these privacy guidelines. That is, the data subject, the person whose privacy we're worried about protecting, they're no longer in the data. They're now fuzzed out, and because of that, it means I can share that information much more rapidly. Rather than someone requesting access to sensitive customer data, and then we've got to go through 3 months of red tape to get them access to the sensitive customer data, and somebody has to manually review that ahead of time, you can now just apply the privacy enhancing technology to that sensitive data set, and the results, which first can be measured for privacy quality and then for data quality and so forth, all can be delivered very quickly Maybe that's to your data scientists who are using that to train machine learning models that they're developing. Maybe that's for data monetization. Maybe that's for analytics. There's all sorts of use cases now that become open to very, very fast, fresh data rather than stale data that's 3 to 6 months old.
Yeah, and I mean, you start to even think about de-scoping some of these systems or some of the data for all of the privacy requirements or different laws, rules, and regulations of the land. So that's interesting then. So what are the key privacy enhancing techniques that actually support this, that make this possible?
Yeah. So there's two broad categories that we can put PETs in right now. One of those is analyzing data in its protected form. And in this case, we're really limited to two kinds of protection. One is called a trusted third party or a secure multi party compute model. And in this, what happens is you share protected data. Some processing is done on that protected data, and the results are then shared back. So person A doesn't trust person B, but they both trust a third party. They can give data to the third party. The third party can do whatever the computation is and hand the results back to the two initial parties. In a secure multi-party compute, each party can add their information to the model, and at the end, everybody can find the answer, but nobody understands what information each party added. These are really interesting techniques, but for the most part, they're still very much on the bleeding edge and useful for very, very specific use cases. Homomorphic encryption is another great example of a privacy enhancing technology that can be used on the actual protected data. In that case, you're able to do mathematical processing of encrypted data without needing to decrypt the data. It's very limited right now. It's also very slow. It's not really ready for the enterprise world. But in labs, it's very interesting what we're doing there. Now, the more common and the ones that are sort of cutting edge but not bleeding edge generally fall into this category where you're removing the individual data subject in some method, but you're retaining the statistical and analytical value of the information. And in this case, it really breaks down into two categories. There's anonymization, and then there's synthetic data. And there are some things that kind of bounce around between the two, like differential privacy. But overall, the goal here is effectively to create an environment where I can learn about the data subjects without actually learning about any one specific data subject.
So let's take those a bit in reverse then. We'll go bleeding edge at the very end. I want to talk a little bit about anonymization and synthetic data. And let's start with anonymization. You mentioned the K, the L, and the T before. For someone who's not a data scientist, right, help me understand a little bit more detail. Like, what is anonymization? What is the benefit? How are those things really helping achieve what you just talked about?
Mhm. So, most of the analytics that we would do on data, we're not really trying to learn so much what an individual is like. We really want to learn about a group of individuals, right? We want to understand trends. We want to analyze so we can say, well, people in this city between these ages really like this product. And to do that, we don't actually need to know all of the specific details of all the data subjects. We need to know the category of data subjects. K-anonymity is a way of creating categories of subjects out of your data set. The K in this example would represent the minimum number of data subjects, individuals in the data set, that would have to have matching quasi identifier. So a quasi identifier is a kind of identifier that you and other people share. Your birthday is a quasi identifier, more than you have the same birthday. Your age is a quasi identifier. Your postcode is a quasi identifier. The city you live in is a quasi identifier. Your area code is a quasi identifier, although your phone number would be a direct identifier. With K anonymity, all of the direct identifiers, your first and last name, your street address, your phone number, your social security number, those are completely removed. And what's left are these quasi identifiers, the kind of information that altogether could still be unique to you, but each individual piece is shared with other people in the data set. When you set the K value, you're saying, I want you to find the optimal generalization of all of these quasi-identifiers such that I end up with groups that have a minimum of k people inside that group. We call these equivalence classes. So inside this equivalence class, if my k anonymity is set to 4, I know that I'll always have a minimum of 4 people inside this equivalence class. The system will generalize, it will find the optimal generalization to fit as many people into the right groups as possible, getting a minimum of 4, and ensuring that we've done as little generalization as possible to get there so that we've retained as much useful information as we can in the set. Now, if we've set a k anonymity to 4, this tells us that, generally speaking, even if I know everything there is to know about an individual, all I could do was say, well, I know they must be in this equivalence class, so they're one of these 4 people. That would give me a 25% chance of re-identifying that person in a best case scenario. So K anonymity is useful because you can really determine very quickly what the privacy level is that you want to require on this data. Is it 1 in 4? Is it 1 in 10? Is it 1 in 100? Is it 1 in 1,000? You can set that configuration, and you can choose where that balance between controlling the privacy is with controlling the amount of information that's lost. L diversity and T closeness are slightly different. Whereas K anonymity is focused on the data subject themselves and the identifiers that might tell us who the data subject is, K anonymity and L diversity look at the other piece of the interesting information in your data set, and that's what we call the sensitive values. The stuff that is important, the stuff that you're probably actually doing analytics on, and the stuff that might cause somebody problems if their privacy was compromised. For example, if it's medical information, that might be their healthcare condition, or what medication they're on, or what they've been diagnosed with. If it's financial information, it might be where they spend their money. In all of these cases, this information, if it is extremely unique, still might allow me to re-identify the individual. Imagine if we have healthcare conditions, and I know that James is in this equivalence class, and there's 15 people in that equivalence class, so that's only a 1 in 15 chance that I might be able to figure out which one is James. But if everybody in that equivalence class had gone to the doctor for a headache, then I would know that James went to the doctor for a headache. Because I don't need to know which one of these 16 people it is. All of them happen to have the same sensitive value. So even though I can't re-identify which one of those records represented James, it doesn't matter. I still got the information that I needed. So L diversity says that there has to be a diversity, whatever number we put in for L, a diversity of possible values in the sensitive value location. So now when the system is figuring out using the algorithm what's the optimal configuration, it has to conclude not only what's optimal for how I generalize my people, but how I generalize my people in the context of what their sensitive values are, so that we have a constant variation in each of these groups. We still end up with highly accurate information from an analytical perspective, but when it comes to trying to identify any one individual or an association between the sensitive value and an individual, that connection is now lost.
So if I am a data scientist and I have the K, L, and the T, I mean, I think part of the power is all of those pieces working together as well, obviously help give you a really data privacy enabled data set. But how am I, or where am I implementing this as part of my data initiatives or my data pipelines? Where does this come into the process?
So anonymization generally happens on a data set. So if my data scientists are interested in training a machine learning model and they'd like to know the behaviors of my customers in dealing with ATMs over the past 2 months, we would go to the real data, wherever that's being stored. We would do an extract of that data through some pipeline process, ETL process, that would pull the stuff that we're interested in learning about. That subset, that new data set that's basically the result of our query, is going to pass through anonymization. have whatever configuration is applied to that, which might be the K anonymity value, the L diversity value, the T closeness value. It may also include priority. We were going to give priority to this kind of column and that kind of column. We want to prioritize age because we're really interested in what seniors are buying, or we really want to look at postcode because we want to know what people in the urban areas are buying versus the suburban areas. So we can pick and tweak all of these little knobs, and the result that we get back then through this pipeline can automatically be processed into machine learning training, for example, or SageMaker, or any of these other tools that allow us to do analytics. So we can just sort of build that right in to the processing of the data itself.
So it just becomes part of the same tools that they're already using then.
That's right. Yeah, it's just
Yeah.
another stop along the way.
No. So you mentioned two topics about removing individual data subjects while still being able to retain that statistical sort of analytical value. Talk to me now a little bit more about synthetic data.
Synthetic data is really interesting. Synthetic data approaches the problem of privacy slightly differently. Whereas anonymization sort of, we can imagine a picture of a crowd of people, and we've fuzzed out the focus just enough that we can't identify any of the specific individuals anymore. In the case of synthetic data, what we've done is we've told a computer to go look at a crowd of people and make me a crowd of people that looks a lot like those people but isn't actually any of those people. And that's exactly what we can do. So again, we can create a data set that has no real data subjects in it, but the data subjects that are there are highly representative of the people in my real data set. That is, statistically, when I analyze those two data sets, they will be almost identical. But any attempt to identify a real person, any one individual person from the real data set in the synthetic, won't be possible because there is no one-to-one, I took this person and turned them into this fake person. It's I took all of these people and turned them into a representation of a bunch of fictional people, a bunch of synthetic people that together create the same kind of mathematical values.
So look at James and everybody like James and give me examples of them without it being James is really the goal. Now, I can see, and from our customers, I have heard how that's valuable around things like test data management, around things like analytics. Talk to me a bit about kind of those two use cases in particular and how you would use synthetic data in one or both.
Test data management and synthetic data is really interesting for certain specific use cases. That is, imagine I want to try a SaaS service. I'm a company. I want to go buy this subscription to use this SaaS service. But before then, I want to make sure this service does what I want it to do. Well, normally they would say, okay, send us some data. We'll load it into our system over here, and then you can do whatever you want to do with your data. But I don't want to give these people my data because it's sensitive customer data. In those cases, I could say, well, instead of giving you these 3 tables of data, I'm going to use a synthetic data generator, generate 3 synthetic tables that look and feel like the real data but aren't, and we'll use those. Now, this isn't a great solution for very broad test data management. So if you're looking at taking a customer from the first time you've met the customer in platform A through the journey of platform B, C, D, and E, and synthetic data isn't going to be able to give you that level of complexity across multiple systems and across time. But if what you're looking for is, if I show you this picture, create a fake picture that's very much like it, that's where synthetic data really shines. Now, in analytics, this is really, really useful. Test data management, if it's a small data set, it's great. With analytics, it means that I can train my machine learning models on the synthetic data, even if I'm going to operate the models on the real data. And in our lab, we found that we generally can get a 95% improvement in the privacy of the data. That is, we go from real identifiable records to a 5% possibility of a similarity between a real person and a synthetic person. But we only lose 0.98% accuracy in the predictive capabilities of the models that we tested. on average. There's a couple models are a little bit more, a couple models are a little bit less, but on average 0.98%. Because the value that the machine learning models are looking for are these trends, are the movements, are the overall broad views of the group. They're not really concerned about one individual. And so because of that, synthetic data is extremely valuable in this space.
So thank you for that. I think before we close down, I want to make sure we give a little bit of time to talk about the other side of the coin, right? You talked about, analyzing data in its protected form. You talked about homomorphic encryption, which is really one of the buzzwords that we hear a lot about. But you mentioned some limitations and others. I'd really like you to maybe give us a little bit more on the current state of where it is today, right? Where it's going. If there are limitations, are there alternatives? Maybe take us through the homomorphic encryption side before we close down.
Yeah. So the first biggest problem that we have with homomorphic encryption is that unlike, for example, AES or FPE, homomorphic encryption hasn't yet found a public peer-reviewed standard algorithm to work with. It's all still experimental. We are still releasing libraries that people can play with in labs to experiment with this concept. It's a really relatively new concept, and it's gone through a lot of improvements. When we were first playing with with homomorphic encryption at Protegrity 10 years ago, when I first joined the company, uh, it didn't perform. I mean, not only it didn't perform, but I would say the numbers are, it's 10,000 times slower than normal encryption. Uh, just this past year, the new Microsoft libraries that have been released are very impressive. They're only about 1,000 times slower than normal encryption. So that's a big problem with homomorphic encryption right now. Is the algorithm speed is just really difficult to make sense of in an enterprise scenario. Another concern with homomorphic encryption is there is a limit to the amount of processing that you can do. For example, fully homomorphic encryption would be the idea that once I've encrypted the data, I can take that data and add or subtract or multiply or divide or whatever. It's not really how it works. At this time, the best that we can really do in any reasonable performance is to ahead of time know we're going to use this for adding, or we're going to use this for subtracting, or we're going to use this for multiplying. And we protect the data so that it will be good for that particular mathematical function and only that mathematical function. Again, in a test in a lab, that's brilliant. That's amazing. Being able to multiply two encrypted values together and actually get the answer out is really cool. But if I've got to, deal with that in an enterprise scenario, it's just not feasible. Um, Additionally, because there is information that's being exposed here, right? If I take this encrypted value and this encrypted value and I multiply them together and I get a result, and then I take that encrypted value and multiply it and get a different result, and if I do this enough, eventually I'll be able to start suspecting what the values are behind those encrypted values. And because of that, it means that after so many queries on the data has to be reprotected because there becomes a risk of information leakage. So homomorphic encryption has a lot of promise, but I think it's going to need another breakthrough or two before it really becomes something that we'll see being used in the enterprise broadly, the way that normal encryption is today.
Well, so this has been really helpful, Clyde. First, I just want to say thank you to you. You did all the heavy lifting here. I really appreciate the information that you've been sharing. Thank you to those that have joined us and for watching another Protegrity episode of our Freedom to Innovate series. Please keep an eye out and look to join us on our next session as well. Thank you. Have a great day.